thrilled with the tremendous turnout for today's presentation. We had over 200 pre-registered attendees. So a couple of announcements before we begin. If you are looking for additional educational opportunities, please plan to join us at the next MD Expo. That's October 1st to the 3rd in Orlando, Florida. You can visit mdexposhow.com for the entire educational schedule and more information. And remember that registration is free for all hospital employees, military, and students. If you can't wait until October to join Technation, then please come and participate in the upcoming CEAI conference this August 20th and 21st in Chicago. You can find out more information about their show at ceaiweb.org. Be sure to mark your calendars for our next webinar, which will be next week, July 30th, featuring Tim Shaver's presentation of Effective Time Management Equals Career Success. And a few last-minute reminders before we begin. A webinar worksheet was emailed to all registered attendees prior to today's call. If you did not receive a copy, you can download it now at iamtechnation.com/webinars. All lines will be muted throughout the webinar, but you can still submit questions during the presentation by using the questions feature on the dashboard on the right-hand side of your screen. If you're having any difficulty, please email us at webinar@mdpublishing.com. An email survey about today's presentation will appear on your computer screen immediately following the conclusion of the webinar. If you complete this survey, you will be entered into a giveaway for a Technation prize pack. Technation would like to thank today's sponsor, Rigel Medical. Rigel Medical is a leading manufacturer of biomedical test equipment, including electrical safety analyzers, vital signs simulators, infusion pump analyzers, electrosurgical analyzers, and asset management software. For more information, visit rigelmedical.com. So let's go ahead and get started. Our presenter today is James Knight. James has spent 25 years testing and repairing medical equipment, primarily in the perioperative arena. He has collected data from his testing and used it to design and implement quality improvement procedures that improve overall medical equipment reliability and reduces parts and labor costs. Okay, James, take it away.
Good morning, everyone. Thank you for your attendance. Thank you to MedWrench and MD Publishing for presenting this, and thank you for Rigel for all the things they've done. I'm going to try to cover in 45 minutes general ESU theory and testing. So here goes. We'll have 4 different parts, we're going to try to really have an emphasis on HF leakage testing, why you need to do this testing, and how this particular piece of equipment called a Unitherm made by Rigel is made. It's much easier for me as a working biomed. I do have I'm a working biomed, and this has really improved how I'm able to do it. So, of course, everyone knows that these are your OR staff usually calls an ESU or BOVI, and we'll explain that it's, the technology that BOVI used a long time ago is no longer in place, and there's a lot of new, exciting, and safer technologies available to you. What is electrosurgery? It's a high-frequency electrical current. It can cut, it can coagulate, desiccate, and fulgurate. There's a few different features that these different modes can provide. There's a bit of confusion, and I'll try to my best to cover the differences between what a doctor means when the device cuts and coagulates and what an engineer means when it cuts and coagulates. Electrosurgery devices are not electrocautery or a diathermy. though the term cauterization is used in ESU devices. Cautery is the heat conduction of a probe. Direct current, a soldering iron is a cautery device. Important to understand is electrosurgery uses alternating current of a high frequency in the 300 to 450 kilohertz range to heat the tissue itself. Coagulation is the sealing of small blood vessels. Often electrosurgery is referred to as diathermy. It's not. Diathermy is dielectric heating. You're familiar with this. Physical therapy have devices that heat the tissue for therapeutic effects. Ultrasound generates waves which do heat the body. As it's a wave that goes out and is reflected back. Your microwave oven is a diathermy device. Electrosurgery is not diathermy. We want to talk about the dangers of electrosurgery. So you have to understand how this heat is produced. As the AC current flows from the intended surgical site to the dispersive pad or across the bipolar poles of a small surgical instrument, there's an excitation that occurs. Some of that excitation is through the tissue's impedance and the resistance to the current flow, and as resistance produces heat. But the majority of this heat stems from rapid vibration of molecules, particularly the water molecule, the H2O molecule. They oscillate back and forth. That back and forth oscillation causes heat. Okay. That oscillation is caused by the changing electromagnetic field. Back in when we first were studying to be biomeds or engineers, we learned about EMF. And E in the physics is the voltage, and H in physics is the magnetic force. We're going to talk about the induced H or HF leakage today. So right now, I need everyone, if they've forgotten about the right-hand rule of basic electronics or physics, to raise your hand, your chat hand, or raise your hand if you need me to go over about how the flow of E voltage produces the corresponding H magnetic field. Just as this is how AC current and DC current produce this field. Does anyone need me to go over that now? We have one hand raised. So, so the right-hand rule, you hold out your right hand and your thumb is pointing to the left, and then your four fingers are pointing up to the top. As E, or your thumb, your E flows in the direction of your thumb, H, a corresponding H, a magnetic field is produced. That magnetic field can induce a current in any ferrous material, any material like iron, metal, just like a transformer works. As the windings wrap around the primary field, the primary winding of a transformer, the secondary winding picks up that induced H field and produces voltage on the secondary. It's the same thing that happens in with the HF leakage from an ESU. An interesting experiment you might want to try is to set up your ESU with a pencil and wrap the hand pencil cord around an 18-inch small fluorescent tube, completely disconnected fluorescent tube. Connect that pencil to your ESU analyzer and discharge the pencil into your ESU analyzer at even a small amount of wattage, and the fluorescent tube will light up. That's because the H is inducing the particles inside that fluorescent tube. It excites them and lights them up. And though there's no direct electrical contact, that's an induced field that happens. Too bad this is just a webinar and I can't display that. So if you have any further questions on that, we'll give you some email references at the end of the webinar. Now on to what's the difference between monopolar and bipolar. I'm sure most of you know this, but monopolar, the energy, the current flows from the active electrode that the surgeon is in control of to either, sometimes called a patient pad, sometimes it's called a neutral electrode, it might be called a dispersive electrode, but that's what monopolar is. Bipolar is when that current passes between a set of tweezers or some other type of small bipolar instrument. Bipolar is inherently more safe because the current flow and the current path is much shorter. So in monopolar, there's the cut mode. And in cut mode, there's two primary methods. There's desiccation and fulguration. In cut mode, tissue is vaporized. HF current passes through the tissue, and the heat of that molecule vibration vaporizes and seals the tissue surrounding the cut tissue. This is one of the primary benefits, and this is why surgeons rarely use scalpel anymore. So how do you differentiate desiccation versus fulguration? In desiccation, the electrode, the pin tip, the pen tip actually touches the tissue. And if the electrode is held over the tissue and the air gap is present, then current jumps that gap and fulguration occurs. Sometimes when that energy that jumps the gap, it's called RF plasma energy to physicists. And also if you happen to weld, this is the same process that occurs during welding when you are using a high voltage electrical welder and the current is jumping the gap. It's known as plasma welding. So now, what happens to the tissue when we are in desiccation mode? Desiccant you find is the little material that keeps things dry in your packaging. So desiccation is when is the state of extreme dryness or process of extreme dryness. So in this slide you see that you're essentially desiccation electrosurgery is produced by low current and high voltage applied over a broad area producing a low current density. That low current density is important. The cells are shrunken and shriveled, and that's important to the surgeon, not so important to us. But cellular detail is preserved. The loss of water is important in certain types of surgery, but we do not coagulate the proteins. Fulguration is a process to destroy and remove tissue. If a doctor is removing a tumor, he wants to fulgurate that tumor. It's the electrical arcs that strike the tissue. He's kind of waving the pen across, and there's localized tissue destruction, and then there's large amounts of carbonization. And that carbonized tissue actually causes an insulation barrier. So that thin layer of carbon and desiccated tissue beneath form an insulating barrier, decreasing the probability of subsequent arc strikes on the same location. That's important for a surgeon. What's important to remember with fulguration is its low amperage and high voltage to overcome the resistance of the large distances between the electrode and the tissue, because the monopolar pencil is actually held above the tissue. So now you see I have a different type of slide shield in there. The slides with the top in blue are for the engineer, and the slides with the scrub tech with a scalper on it, that's more the physiology or the clinical or the surgeon side. So what I want to point out here is this is what a coagulation waveform looks like, and it's used to perform hemostasis. Hemostasis is the process of sealing blood vessels and general other vessels also. You notice that there's a sine wave, but the amplitude of the sine wave slowly increases and slowly decreases. That's the important thing to remember about coagulation. So this is what coag. Remember we talked first about cutting, and in monopolar there's cut and coag. So what kind of tissue effects occur in coagulation? Well, this is when we need to form blood clots. It's an important part of hemostasis. The stopping of blood loss from a damaged vessel, if the surgeon is performing surgery on a trauma victim that's been in an automobile wreck, and they need to stop the blood bleeding, and they coagulate. Okay. Technically, the platelet and the fibrin-containing clot stop bleeding and begin to repair the damaged vessel. Okay. This coagulation is completely different. It's a high current density, much higher current density than desiccation, and that's achieved by the slowly amplitude rising of the RF energy. The tissue actually boils, and proteins become denatured, forming a white coagulum similar to that when an egg white is boiled. So you know what happens, a hard-boiled egg, it's no longer runny, it becomes a firm jello-like substance. That's what happens during coagulation. The cellular definition goes away. It's formless. It's no longer unique, homogeneous. This is what's known as coagulation necrosis. So now I'm going to sum up these differences, okay? ESU modes and surgical objectives. When we're testing during our PMs, we have to test the ESU in monopolar and bipolar, cut and coag, and several different modes. Those different modes are also the same words that surgeons use, okay? So surgeons have categorized ESU modes by the changes to the structure of the cells. When we're doing a PM, we don't see any cell structure changing. But you have to remember that the key difference when you're talking to a surgeon or a nurse, that they're looking at desiccation and coagulation from the point of how it changes cell structure. They also talk about the type of cut the different waveforms produce. So they're interested in either fulguration or vaporization. Electrical engineers and biomeds, we categorize ESU modes by the shape of the waveform. A cut waveform is a pure sinusoidal, and a coag has a very unique waveform, which I will show you shortly. But both coag and cut have desiccation and fulguration options. So it's important that you keep in mind when you're talking to a surgeon versus when you're talking to someone in tech support about what is cut and what is coag. A pure cutting current is very easy to recognize. It's a pure sinusoidal waveform. There's no variations in the frequency or in the amplitude. But when we coag is done, remember, coag has to achieve a higher current density. So the frequency gets higher, and so does the amplitude modulation of that frequency. So the waveform gets narrower and then wider, and as it gets narrower, the amplitude increases. So here's an actual oscilloscope capture of a full duration waveform. Notice that the amplitude of this waveform is uniform in its change. It increases and decreases, okay? And also, if you notice, the frequency is very uniform. If you notice that at the very left-hand side, there's a negative going pulse, and then it's of slightly longer than the next pulse, which is positive, and then the next positive pulse is even larger, and then we go small negative, and then even smaller negative, then increase. What they're trying to do there is fulgurate the tissue. So they've greatly varied the pure sinusoidal waveform, and they've greatly varied a standard coagulation waveform to achieve a desired physiological effect that the surgeon is asking for. So here's the blended currents. Okay, when you see the blend option, you notice that there's the variance, but in between the varied amplitude is your standard cut waveform. Now, this is the toughest waveform. It's the most complex waveform, and you need to know this, because this mode creates the greatest amount of HF leakage. Even though the coag wattage might be only 120 watts, and a cut waveform at 120 watts produces much less HF leakage than a coag waveform at 120 watts. I'm going to say that again, and I'll show you a chart later. Compared at 120 watts, a coag waveform produces much higher HF leakage than a cut waveform. And that's because it's much easier for the electrical engineers to design a tank circuit that sends the stray H field, the induced HF leakage, to ground when the waveform is constant and steady. You see how much this varies? Every single pulse changes in polarity, and every single pulse changes in amplitude. And if you notice, it's clearly visible in the third from the left graticule that the frequency is also changing. So it's very difficult to design a circuit that will take the induced H, the HF leakage, the induced magnetic field from all of the other metal surroundings, and try to bring that, try to effectively send that induced voltage to ground and keep it out of the surgical arena. So I hope I've explained that. And again, you'll get my contact information and Rigel's contact information. But I hope I'm explaining, and feel free to raise your hand if you have a question about this. But I'm trying my best to explain why you really need to do this test and why it's so difficult. So, we've explained electrical surgical history and theory. Now the standards. We're all biomeds. We all know we've got to do the manufacturer's test, but we're going to concentrate just on this one thing called IEC 60601-2-2. This is the HF leakage portion of this. So everyone has slightly different hospital EOC policies to follow. You might be following AMI, you might be following IEC, but look up in your EOC and see what policy you follow, okay? There's a minimum safety requirement specified in the standard, and I'll give you some examples of what happens. But anyhow, first we'll talk about this is a typical PMI, performance preventive maintenance inspection from ESU. You want to check the power output. Ideally, you want to check it in current wattage, voltage of RMS, or voltage in peak to peak, depending on what the manufacturer specifies. I'm going to quickly show you, this is what the Valley Lab Force FX PM I've quoted right from the manual. And if you want this sheet, this condenses about 17 pages into what you actually need to do. So you need to set your analyzer load to 100 ohms, and you set the bipolar power of 1 to 10, and then you test it in all 3 modes. And in Valley Lab, they ask that you measure the current. It's so interesting when I go around to hospitals, I see people are still putting stickers that say wattage. Valley Lab really isn't concerned about wattage, they're concerned about milliamps. And there's a good reason for that. Now, not all manufacturers are like that. The ConMed Sabre just wants you to check what the wattage is delivered. And so here's an Excel sheet, and they just want you to know what's the wattage delivered at 50 watts. They're not interested in the current. So it depends on manufacturer. You have to look at your PM book and study it. But it's important to know that not all manufacturers, in fact, it's less and less want wattage and more want current. Here I have the Valley Lab PM spelled out in this slide presentation. Here's what the Valley Lab PM says to how to check the high frequency leakage current from Monopolar. You have to connect a 200 ohm load from the active accessory to a current transformer to the equipotential ground level of the generator. So you have a series circuit, and then you put the current transformer to a 2 RMS, and then you activate it at the maximum control setting. I used to do it with an external 200 ohm load, but I burned myself once, and because there's quite a bit of current going through there. If there's anyone else in the audience that's ever burned themselves, I can understand because that this external 200 ohm load, if you accidentally get your hand too close to that resistor, the current will go to you. But we all have stories about that. So here's the HF leakage portion testing. Okay, you got to ensure that the ESU circuitry is properly limiting the amount of capacitive and inductive leakage of high frequency current. The higher the frequency, the better that current can travel. As you know, if you're working in Wi-Fi, you know, we found out that the higher the frequency, the further that those devices are able to send their signal. Stray current has been scientifically demonstrated to cause harm. I think Amy first published that in 1992. So I cannot display the copyright material in 60601, but I'm showing you that go to 19.3.101 and read about the thermal effects of HF leakage currents. So I've put the first few first sentence, and then I broke up and included the last sentence. But I can't display that in my PowerPoint without copyright violation. This is the actual Amy's wording for it. And I'm just going to ask you to go to Amy and read that. It took a long time for me and a lot of practice just to understand it. The wording of this wasn't really easy for me to understand, or any of the biomeds I worked with. So it took a long time for us to actually understand what this meant, figure out what HF leakage testing actually required. But why should you test it? Well, you know, there were 615 claims associated with laparoscopic procedures using electrosurgery. Now, the insurance companies are not going to tell you what the exact damage was, but a majority of the claims resulted from thermal damage to unintended patient tissue. That's all we could get out of them. You know how lawyers are and hospitals are. So what kind of problems happen? Well, there's a risk to the patient. Capacitive coupling can be in part responsible for serious patient complications. Now, manufacturers go to great lengths to minimize this. So they put active electrode shielding. They use dispersive metal cannulas. They use sheath guide wires. And one of the easiest ways to do this is to use bipolar active electrodes. A bipolar really narrows down the area where the current flows. And when you have such a localized application of RF energy, it's much easier to reduce the risk that way. So that's the benefit of bipolar in a nutshell. What kind of problems can occur? We can have HF interference to other medical devices, implanted medical devices, class 3 medical devices. You can have endoscopic camera images. I'm probably about once every 6 months, someone emails me and tells me, hey, when I operate this particular, when the ESU is being operated, I lose my endoscopic image on my ancillary monitor, not the monitor that's on the video card, but the one that's cabled up and goes across the room for the scrub tech to look at. And we usually find out that that there is excessive leakage on that ESU. It also happens on the in-room viewing cameras, those IP-based cameras that let the nurse manager view what's going on in the room. Those are very susceptible to HF leakage. And occasionally, the shielding on a EKG lead on a patient monitor will go bad. And then any stray current, even less than the maximum allowed 150, will cause a noise on the ECG monitor. So I did not mean to do that. So what type of problems? Well, there's direct and indirect. Now, I'm going to show you about direct, but there's nothing we can do about direct, but I'm going to define that for you. But here back in 1992, Amy publishes a great magazine. I'm sure many of you get it. It's called the Biomedical Instrumentation and Technology magazine. And in 92, they identified, and so I quote that if you want to go through your archives, capacitively coupled currents have been documented and quantified. So here's two cases, but they figured out that, wow, we need to start paying attention to this problem. And that was 22 years ago. Okay. How many current? I got a question. So how many of you currently do HF testing? So I guess type into your chat list if you do or you do not, so we can answer that question for that seminar attendee. So, what is tested? HF output current from the active and the dispersive electrode. You have to test both of these because both of these are conductive paths. Both can produce the unwanted H or HF leakage. When the tests are done, either the active electrode is left open or the dispersive electrode is left open. That's testing of simulating a failure, just as the same way when you do electrical safety tests on all your pieces of equipment. You push the ground, the open ground, you're simulating the failure in the ground pin just so you can simulate a failure and see the worst case scenario. Real simply stated, you should not exceed 150 milliamps. This is a diagram of indirect coupling. In the bottom of the equivalent circuit, the thing that says voltage N, that's your RF generator, okay? And then the thing that looks like a transformer and labeled M, it's not a transformer. This is just what happens when you have stray HF current. So the VN on the top is the active electrode. The resistor on the bottom is the human biological tissue that we're applying the ESU RF energy to, and then on the left-hand side of that resistor is the dispersive pad. Induced voltage travels to voltage secondary. See where on the right-hand side, the circle with the sine waveform and the voltage S and the RL. That's where we don't want voltage and current occurring, and that's why we're testing these devices, because we have to make sure that that is a low current. Now, here's a long explanation on direct coupling. Unintended contact with a conductive surface. Again, email me for this slide. You can't do anything about this as a biomedical engineer. This is what happens when a surgeon makes a mistake, direct coupling. Great. So how to test. I used to use the method on the left-hand side. I used a true RMS voltmeter and a current transformer and a large-scale non-inductive 200-watt 1% resistor. But now I use the LIGO Unitherm. You see, this is a diagram of how really easy it is. And this diagram, the right-hand image, shows that we're connecting the neutral or dispersive electrode to the ESU analyzer. And those round black things are jumpers. And so we're connecting a 200 ohm load to earth ground, just as the regulation tells us to do this, while the active electrode is open. And so remember that the manufacturers specify that you test with active electrode open and neutral electrode open. So again, I bring this back up. This is what Valley Lab tells us to, COVIDing, sorry, it tells us to do that. You can connect a transformer, or this image shows the Unitherm. That black banana cable is coming directly from the either the active electrode or the dispersive electrode. You have to test both, and it follows through the white. There's a direct connection there. If you want to look at, that's how I got the waveforms, is plugging into the scope output there. And then this bottom half-circle jumper connects the 200 ohm load right there, and it helps people with really big hands like me from not touching that exposed 200 ohm resistor. Anybody know how much current comes from a triad ligature test when you're doing the triad ligature test on HF leakage? How much current is going through that 200 ohm resistor? This is a slide of the unitherm actually telling you what to do. You select monocut, you set it to 300 watts. The unitherm fires the device, and this is what the result looks like. It tells you it's passed. Good. So we're done in 40 minutes. If you want a complete thorough guide to electrosurgery, you can email this email address, and this guide is it's fantastic. It'll let you look at it a lot of this information at a more thorough pace. Jose asked, do you have a diagram of when you use the ESU 2400 by DC Biomedical? I do, but I don't have it handy. The hospital I worked for actually, sorry, you've asked, this is the truth. We bought the ESU 2400, and it was difficult to use, and so then we bought the. This isn't supposed to be a commercial for Rigel, but I can do a Force FX PM, a full PM in 18 minutes, every single thing, and I can. That's every test, and I'll show you what that test is. And it took about an hour to use the 2400. So we have a 2400 that's just gathering dust, and that's the truth, It was too complex to use. There's also a question from Manuel. Let me see, Manuel. Looking for you. Manuel asking, are the biotech RSVO2 still usable in today's market with such a, that's definitely a sales question. I'd ask Jack that. I have my opinion on that. All I can say is that I work at the largest trauma hospital in Northern California. We took care of some major accidents, and when that airplane liner crashed, we were absolutely full, and we needed every single one of our ESUs. And so we've got a lot of ESUs, and we have to test a lot of ESUs. And here, I'm going to show everybody. This is a template. This template right here is what we use. This does a Valorab FX. Line 5 is the low mode, line 6 is the medium. So this does every single test. And now I'm going to show you what a test. So that's the test output right there. The power delivered, the current delivered, and even the REM. You see all the different HF leakages that we test. So, and then, just for interestingness, I've been tracking where the highest leakages are. And so you can look at that while I read some more questions. Biotech RSVO2, not bad, but I really like the 454, and I was really sad we traded in the 454 when we got the 2400. And then, then we were really disappointed, and we wish we would have kept that 454. But now we're able to do these PMs way faster because of the automated test sequence. Let me go back. Jose. Russell asked, why was the triad limit 200? I thought, well, that's a good question that Covidien, you have to ask Covidien. I think what, Russell, you're asking is, in the school, the limit was 200, but in the published diagram, it's, in the published service manual, it's 150. And I don't work for Covidien. The people at Covidien Tech Support are fantastic people. Give them a call, and they'll straighten that out. I do know that performing a triad PM takes a long time, and it's really sped up when we when we started using the Unitherm. Another question. I use the auto program to test a triad. I want to make a program for the Force FX. Yes, so that template I showed you right here, this is the result of a Unitherm. Everything I'm going to highlight right here. So this is the results that you can download directly from the thumb drive once you do your tests. So everything that's not highlighted right now, I just use that template, and I fill in the control number and the tested. You know, I think I have another. Sorry. Let me see if I open up this. It's going to take a while. So here's the triad. I don't know if you can read that, but doing a triad test takes, I think I've got this down to 35 minutes. It was taking us 3 hours before. We're down to 35 minutes due to the sequencing. But this is the literal result. You know, the Unitherm actually tells you down to the seconds. This field right there, you enter it. This is the test sequence, and you've got to test the bipolar load in 3 different wattages. So you have to test 3 different loads and 3 different wattages. Then you have to test the coax grade, the Valley Lab mode, triad, the pure cut, the monopolar, the HF leakage. There's the HF leakage. Let's zoom in on that. These are the results. So the triad leakage. You notice that didn't mean to do that. Thanks. Anyhow, I'm going to show you one more thing. I should put up my email address reading these questions. Never too old or too young. That's my little 6-year-old. He's already training him to be a biomed. That's my email address. And I'm real interested in just sharing what you know. Oh, I see. There's a clarification. The analyzer is set to 200, but yeah. So I see. Rigel has a default of 200 milliamps because they're worldwide, but you can set it to 150. There's one question. Ryan asked, why should you look if your HF is too high? So Ryan, the reason you need to is the interference it causes to other medical equipment and the potential harm that it can cause. So if your leakage is too high and if the nurse has coiled the ESU 10's cable around a pole on the OR, and they coiled it around, she's created a transformer. And the surgical table has a whole lot of ferrous, iron, steel in it. And if the patient is touching any portion of that metal table and the ground pin on that metal table power cord is broken because plant maintenance takes care of doing the electrical safety tests instead of the biomed, which is true in a lot of hospitals, then that induced current from the HF leakage will flow to that patient's hand or whatever portion of that of the body the patient's touching. And it will cause a burn there. HF leakage causes burn and electrical shock. HF leakage is, we all use our electrical safety testers to test for a type of leakage, and it's considered DC leakage. It's from 0 to 60 hertz because the power we're using, the power of the equipment is 60 hertz. It's much easier to create a circuit and to shield 60 hertz. Okay, ESUs generate 300 kilohertz to 450 kilohertz. Much more difficult, and you're applying this to the body. Any stray 300, 400, 450 kilohertz signal can cause electrical shock or thermal damage. So I hope I'm answering your question. Question from Ryan. What to check? Why not to check? Ryan. Oh, Ryan said, I'm asking what should you look to repair if it's too high? The very first thing you should do is you should call the manufacturer. You should call tech support. The second thing that I have found, one thing is on a Force FX, I have found that a return electrode monitoring pad socket was cracked, and that was giving that was causing the problem. Again, I'd love people to email me and tell me about their specific incidents so we can compile this information and pass it on. The next question, does your analyzer print out those? No, it saves them to a USB stick. There might be a way for it to interface directly with the software program, but we don't use the Rival software program. We use TMS. That would be a good thing, but that doesn't happen. Let's see. There's 113 of you out there, and I'm scrolling through all the questions, and I hope I've answered them all. Yeah, we have, Rigel has a FX test sequence. We've demonstrated this at other hospitals. We've timed it. I think an average biomed could do the full test in under 20 minutes, the entire test, because, and you know how much they all want you to do more. Everyone's asked, all of our biomed managers are asking us to do everything faster, in less time, and do more. Okay, so I have a test. What about testing ligature mode in the triad? Yes. So you do that ligature test. Let me see if I can find something here. I want to take up it. It's going to take a little bit of time for me to find that. The answer, I had a question, is how much current, when the ligature is set to full wattage, how much current is coming through that? It's 5.5 amps. That's a lot of amps that you might not realize. So I'm going through my test results. The triad has so many Got it. Got it. So there's the China registry test. They ask you to set it. It's a variety of testing. This is the results. That's the current. There you go. So hopefully I've answered that question. Oh, I've got to get rid of that. So I have a question about the bipolar test. What's the specific load resistance? Very often it's 100, sometimes it's 50. You have to refer back to the manufacturer's guidelines. The ConMed Saber, which is a very popular device, uses 50 ohm load for its test. The Covidian Valley Lab uses 100 ohms. You have to use manufacturer's guidelines for that. So we're coming up on an hour. Any more questions that I could answer to you right now? Or do you want to email me?
Okay, James, thank you so much. I think if anybody else has questions at this point, we'll let them contact you directly, or you can also make comments on the survey that will appear immediately following the conclusion of this call. Remember that if you complete your survey, you will be entered to win a Technation prize pack. And one final thank you once again to Rigel Medical for sponsoring today's webinar. Without the support of our sponsors, we wouldn't be able to host this free webinar series. So thank you all for your participation. We appreciate it, and we hope to see you right back here next Wednesday for Tim Shaver's presentation. Thanks, and have a good rest of the day.